Hey guys, how's it going? Hope everybody's staying well and as happy as they possibly can be, considering the situation. We're going to do a PowerPoint here. I'm not used to doing this sort of thing, so bear with me. It won't be Hollywood production quality, but I'm sure it will be fine enough. You might hear a dog barking in the background. That's my dog Cooper. He may come visit us from occasion. Anyway, we'll move along with this. We're going to do chapter 6, end of chapter 6 today. Okay, so the very end of it, we didn't get to a couple weeks ago. I guess it's 3 weeks ago now. So we're going to do the pulse averaging discriminator, quadrature detector, and the phase lock loop. Okay, now make sure that you have the Canvas app loaded on your PC or on your smartphone, because that's how we're going to talk from now on. I've got a discussion group open there and some announcements. So hopefully you saw all the announcements. We have an exam in about, I think, 2 weeks, so we'll talk about that next week. We'll do chapter 8 next week. This will finish up chapter 6. Make sure that you keep doing your homeworks and so on. The discussion group is 4 questions. If you want to ask questions between each other or me, just do that. I'll try to stay on top of it and answer within a few hours or a day. Okay, so here we go, I think. So what is a pulse averaging discriminator? All right, here's a block diagram of it. I'll back this. It has a zero crossing detector, a one-shot, all right, and then this is a filter. Okay, so that's what it consists of, all right? And the one shot, or the zero crossing detector, takes the input signal, which is a FM modulated signal, and basically clips it. It uses it basically does a zero crossing detection. So it turns it into a square wave. So here I've drawn this, or copied this out of the textbook actually. Here's your FM wave, right? So you see it's higher frequency here, lower frequency here, and higher frequency here. And the zero crossing detector, B spot here, outputs a, not a square wave, but a modulated square wave. Okay, so it basically takes a sine wave and turns it into a square wave, which is frequency modulated, all right? Zero crossing detector is usually like a comparator or something like that. Then we go through a one-shot multivibrator, which takes each rising edge of this, you notice, and turns it into a fixed width pulse. That's a one-shot. It's like a 74-123 or something like that, TTL device. So you see these series of pulses coming out of here, right? And then that gets fed into a low-pass filter. Now that low-pass filter basically is a charge pump, I like to call it. It charges the capacitor. And that capacitor is going to get charged more often the more pulses come along. So the pulses in this area are spaced apart. Pulses in this area are closer together. So the more often that capacitor gets charged up, the higher the output voltage is going to be. You see that right here? More pulses closer together, you have higher output voltage. Same over here, okay? And that results in your demodulated baseband signal. So here's the input FM. So high frequency corresponds to a high voltage, low frequency corresponds to a low voltage. So we're actually doing FM demodulation. So we were going to do a lab on this. Unfortunately, we can't do that now, but the lab actually works very well. We actually have a zero crossing detector, a one shot, and a low pass filter, and it works pretty darn well. And we were going to use our FM modulator to as the source. Okay, but use your imagination. Hopefully, this won't be too much of a burden on not having labs. It's kind of a bummer, but we got to do what we got to do. Okay. So if any questions on this, look at the text. Please keep your faces in the textbook. It's really important. And obviously the discussion group on Canvas. Okay. So there's another demodulator, which is a quadrature detector, and that's a really really popular way of demodulating FM signals, used in TV a lot. Okay, it uses a device called a phase detector. Okay, so the phase detector is a device that, the way I like to describe it, it likes to see signals coming into it, which are two signals, A and B here, that are 90 degrees out of phase. So A is 0 degrees, B is 90 degrees, or whatever. They're 90 degrees out from one another. The output of the phase detector, all right, outputs what's called an autocorrelation signal. You don't have to know that, but that's what it's mathematically what it's called. It is a mellow, kind of low amplitude signal, okay, at a certain voltage when the signals are 0 and 90 degrees out. All right, so one is 0 and the other is 90 degrees. Okay, when they are not like that, when those two input signals are not 90 degrees out, the output signal gets higher or lower in voltage. Okay, so it basically generates an output voltage that is, but it's also, it's kind of an AC voltage, but it's got a DC component to it. So it kind of looks like a triangle wave, but it has a DC component to it. And that DC component rises and falls with what that corresponds to the phase of the input signal. So for example, if they're 90 degrees out, you'll get, let's just use for an example, you get a volt out. If they're not 90 degrees, let's say they're 60 degrees out, you might get 3/4 of a volt output. If they're not 90 degrees, but they're 120 degrees, you might get 1.25 volts out of your phase detector. Make sense? Okay, so the whole job of this thing is to determine the phase relationship of these two inputs. Now, this low-pass filter filters out all of that autocorrelation signal, or the triangle wave stuff that I was telling you about, and only outputs the DC component, okay, which corresponds to the phase of the two signals. Now, we had talked previously a few weeks ago about FM being indirect, or phase modulation being like indirect FM. Okay, it's hard to tell the two difference. And this phase detector doesn't know the difference between those two things. It sees a difference in phase as FM is happening. So as FM is happening, as frequency modulation happens, you get this phase difference between the two on a time basis, a time-to-time basis. So at one period of time, you get one phase relationship, another period of time, you get a different phase relationship. As on this, particularly on this tank circuit, okay? So at resonance, at perfect resonance, this circuit will produce 0 and 90 degrees on these two inputs, okay? That resonant circuit, this tank circuit, is tuned to be the same frequency as the carrier frequency or resting frequency of the FM input, okay? So that's the resting frequency. So if you have no FM at all, in other words, the resting frequency of the FM, carrier frequency, you'll have 0 and 90 degrees. This is not doing anything, this output. It's just sitting there at a voltage, all right, no AC. But as soon as you start moving the FM, in other words, moving it away from the resonant frequency, which is FM, right? Then you get some discrepancy between the two input signals, which produce an AC signal out here, a varying signal, which corresponds to the baseband signal, okay? So hopefully that makes sense to you. Now this phase detector, we're gonna move on to the next section, which is a phase lock loop, okay? Let's see if I can do that. Yeah, phase lock loop, we were also gonna do a lab on this, all right? Now, phase lock loops are really important circuits. All right, they're used in everything. They're used in your cell phones. They're used in your computers. They're used in pretty much they're everywhere. They're ubiquitous, as we say. And basically, what they are frequency synthesizers. They'll take one frequency on the input, and they'll create another frequency on the output. Now, in the process of doing this, it creates other error signals, which we can use for demodulation. So I think I've got a picture coming up here. Yeah, okay. So here's a phase lock loop. Okay, this is a block diagram of a phase lock loop. You have your FM input. You have another phase detector. This is the same phase detector that's used in the quadrature detector. Or yeah, quadrature, same thing. Then we have a low pass filter. Again, very similar. This is basically a quadrature detector right here, these two parts. Now the difference is, let's ignore this recovered modulating signal for a second. You have this loop. This comes back, and then in the loop is a voltage controlled oscillator. Okay, so this voltage controlled oscillator, as we've talked, is a device that produces a signal, a frequency right here on the output, which corresponds to a voltage on the input. So what we do is we feed the output of the low pass filter, which is, as you know, as we talked about in a quadrature detector before, it's a DC voltage, okay, corresponding to the phase of these two inputs. So if this is 0 degrees, this is 90 degrees, okay? This phase detector coming through the low pass filter produces a steady DC voltage, which therefore controls the VCO. Now, if these are not at 0 and 90 degrees, these two inputs, what happens is the phase detector is not going to be happy, and it's going to start producing voltages here. And it's going to boss around the voltage controlled oscillator to the point where it's going to force it to create 90-degree phase relationship between the input and the looped back VCO output. Okay, so it's a control loop. All right, so if they're not 90 degrees out, let's say they're 80 degrees, it's going to be a lower voltage. So it's going to change the frequency here of the VCO to force it until there's a 90 degrees relationship. Once there is, the phase lock loop is what we call locked. Okay, that's a locked phase lock loop. And once it's locked, any variation on the FM input will steer the VCO frequency output, okay, to keep these two signals 90 degrees. All right. Now, in the process of doing that, it creates a control voltage, or an error voltage, we call it, right here on the recovered modulating signal. That error voltage corresponds to our recovered baseband signal, recovered modulating signal. Okay. So if you were to see a question on an exam, I'm not saying it's going to happen, but if you do, you're going to say that the recovered modulating signal, the demodulated signal in a phase lock loop, comes out of the low pass filter. Okay. Again, there's three parts to a standard phase lock loop: phase detector, low pass filter, and the VCO. Okay. Now, see what else we got here. Yeah, so this sort of talks about, in words, what I just talked about. It generates an error signal, compares it based on the two input signals. If they are out of phase, meaning not 90 degrees, it will create an error signal, all right, and adjust this VCO frequency in an attempt to correct for the original frequency or phase difference. And this keeps talking about what I was just wording out, okay, so you can read that. Now, this is kind of important down here. When there's no input, the VCO operates at a free running frequency, okay. You try to make it so that the free running frequency, in other words, you try to design the phase lock loop so that the free running frequency is at the resting frequency of the input. Let me go back a second. Okay, so here's your FM input. Let's say you're at the resting frequency, meaning there's no modulation. So it's just the carrier, okay? All right, so this VCO, the free running frequency, we try to make it so that it sits at the same frequency as the input when it's resting. That makes the phase lock loop lock quicker because the phase detector doesn't have to do as much. They're the same frequency. So all it has to do is wiggle the, the VCO a little bit just to slide the two inputs, these two inputs, so that they're 90 degrees apart. You would have seen this in the lab. It's a great demonstration on two-channel scope, and you would have seen it. So I'm kind of bummed that we didn't do this, but you kind of can draw a picture in your mind of it, hopefully. So anyway, that's the free running frequency. All right. Now the process, I think the next slide, yeah, the process of locking the phase lock loop. Okay, there's two ranges. One is lock range and one is the capture range. Okay, so when the phase lock loop is not locked, okay, when the two inputs are not 90 degrees out, meaning the phase detector has not been able to boss the VCO enough to get everything locked in to 90 degrees. All right, it's moving the error voltage all over the place, trying to get that VCO to line everything up to 90 degrees, line its output up to 90 degrees with respect to the input. That frequency on the input, all right, might go from over here, this lower end, to the upper end over here. All right, so I should say that the VCO frequency might be ranging from in here, or it could be the input frequency, either one. A lot of times lock range refers to the input frequency. All right, all right. Now that's after it's locked. This is the range that it'll stay locked, okay? So now when it's not locked, that's the capture range. So basically it's not locked. You have to get closer to the free running frequency on the input, okay, in order for the phase lock loop to capture and lock. So there's two processes here, okay? You have the lock range after it's locked and the capture range before it's locked. So before it's locked, your input frequency has to come within this range. And this could, let's use some examples. Let's say this is 1 megahertz, the free running frequency. And let's say the capture range goes from 1.2 megahertz to 800 kilohertz. All right, so the capture range is going to be 400 kilohertz, right, on either side. 200 this way, 200 that way. All right, so you have to get within 400 kilohertz of your 1 megahertz in order for the thing to lock. All right. Now, once it's locked, you can move out beyond your capture range. You can move beyond that 400 kilohertz. You can go maybe 300 kilohertz this side and 300 kilohertz below. So 700 kilohertz to 1.3 megahertz. And it'll stay locked. All right. Now, once you get beyond that, beyond the lock range, it'll go out of lock. And then your phase detector cannot generate enough voltage to, or the VCO cannot generate enough range of frequency in order to create a locked phase lock loop. So you have to bring in your frequency back down, your input frequency back down to within the capture range in order to relock it. Okay? So that's capture range and lock range. So just remember, capture range is always smaller or not as wide as your lock range. Okay? All right, so there's one other concept on phase lock loops that we're going to talk about. Okay? And that is this basically, it's a phase lock loop that has dividers in these two branches. There's my dog here. In these two branches, okay? First of all, this one, the first one, is a divide by R, all right? And what that's going to do is divide the input frequency by that amount. All right, so basically it's the same thing, only your output frequency here, okay, if we ignore this for now, just ignore the end for now, just say this is looped in. Okay, go lay down, go on, go lay down, go on, go lay down. if you divide, if you just pretend this is a wire for now. If you divide this by R, what happens is your output frequency, okay, of your VCO, it's going to be identical to this input frequency, and so it's going to divide the output frequency, right? So like, for example, we have 1 megahertz in here, divide that by 2, you're going to get 500 kilohertz on the output, right? Okay, pretty straightforward. Now, here's the other thing. This is cool. So if you put a divider in the feedback loop, what happens is, okay, is the output of the VCO, all right, which is the same as this FVCO, comes out, goes into the phase detector, and it's slowed down, all right? So what does the VCO have to do? It has to speed up its output frequency in order to compensate for this divider. So let's drop this one for now and have just the input go straight into the phase detector without a divider. Let's say it's divided by 1. Okay? All right. So if this is divided by 2 and you have 1 megahertz coming in here, okay, 1 megahertz comes through here, goes through the VCO, gets divided by 2, gets 500 kilohertz. Well, what does the phase detector do? It says, oh, I only have 500 kilohertz here. I need to ramp up that VCO to 2 megahertz in order to make this output of the divider 1 megahertz to match the input. So now they're both 1 megahertz. So we have 1 megahertz here, 1 megahertz on both inputs of the phase detector. It's happy. And they're 90 degrees out because it's adjusted for the loop, through the loop filter, adjusted the VCO phase. What's the output frequency? It's 2 megahertz. So you've done frequency multiplication. All right, so frequency multiplication is being done by putting a divider in the feedback loop. All right, now if you do a divider in the input and a divider in feedback loop, you now have an equation which is your FVCO, all right, multiplied by N divided by R. Okay, so that's fractional multiplication of your output, all right, VCO output frequency. All right, and this is how frequency synthesis is often done, okay? It's done in the digital domain now, okay? So this loop filter is a digital thing, and so on. But essentially, this is the principle. All right, so that's the end of chapter 6. So I'm going to post this on, I might make a couple edits, but I'll post this on our Canvas site under media probably. And please participate in the discussion if you can, if you have any questions. And as I said, I'll try to answer that as quickly as I possibly can. Okay? Good luck.